first of all, I'd like to thank Ken and Charles for the invitation. When I received this from Ken, it was like, Dick, do you know anything that actually worked because it wasn't supposed to, or failed because when it was supposed to work? Being somebody whose highest piece of technology is a hammer and a hand lens, that proved to be a bit of a challenge. But anyways, what I thought we'd do, if we could put the talk up, Tosdal, what do I need to do?
He's working on it.
Yeah. And so I thought about it, and I said, okay. So we just finished a big project that was sponsored by some of the mining companies, and I thought I'd take a geologic aspect about some of the rock geochemistry that we worked on, and really the question is asked is, sometimes you find the low temperature Pathfinder elements, or elements that are not supposed to be in the middle of a porphyry copper system there. So if you're doing a soil survey or something, then you might use that to think about what some of the geology is. So my addition to the title is with geologic knowledge, because technology alone is fantastic, and as Ken has described in the paper for the ASEG, it may not help you find something. So back in the background, that's the outcrop at Reko-Dik in Baluchistan, westernmost Pakistan. Iran is just a few kilometers on that way, and Afghanistan is just a few kilometers on that way. And the Paki geologists love to greet you and say, welcome, we are the Taliban. Because Taliban is the word for students. Okay? It's not terrorists, it's students. All right? Okay, so let's go. So we got one of the premier exploration geochemists in the audience, and he'll probably run me up and down the side of the rooms at the end of the talk. But soil and rock chip geochemistry is one of the really tried and true methods of exploration. Okay? You now, with some new field-based instruments, the shortwave infrared and the PXRF, you can actually get some really quick returns on your geologic information in real time. And they are really good at allowing you to expand the footprint, be able to see the edges of a porphyry system much farther away than we used to. But the use of the geochemical data is really, really uneven. In a lot of cases, even for someone coming from the geology background, they wouldn't know an element bit them in the foot. It's really restrictive. People will look at just a half dozen, 2, 3 elements, and that's it, and won't really use the periodic table, which provides you with an additional whole suite of geologic knowledge. But we know in a hydrothermal system that elements are distributed along temperature and pH and redox gradients, and et cetera, et cetera. In a lot of cases, the geology is forgotten, and you just go drill the anomaly. It's particularly true in a covered terrain, of course. Okay, so I'm going to go back, because I know there's a lot of varying backgrounds in the audience, some of who deal in number space and some of them deal in rock space. So I thought I'd do a bit of review of a porphyry system, and the main emphasis is there's really 2 fluids that are present. One which is the magmatic juice, which is coming out of, I forgot to turn the batteries around, that's coming out of the magmatic cupola down here at whatever depth, 3 to 5 kilometers paleo depth. It's being focused up along the porphyry intrusions, and as it rises and interacts with the wall rock, it cools and changes composition, etc. That's the magmatic fluid that comes up like this. At the same time, you put this big Bunsen burner into the earth crust, and that is driving a circulation of a large-scale geothermal system, which, depending upon the rock compositions, will come up with a different fluid. And at times, along the margins, you'll have an interface, in this case from Mount Milligan, where you have the Potassic chalcopyrite biotite alteration, and it's being overprinted by the sodium calcic. So that's the magmatic juice and the external fluid, and that is removing out copper, whereas this is precipitating copper. Okay, this is the alteration assemblage. I won't go through it. Everybody should have it imprinted in their mind. The magmatic comes up, fluid goes up the middle, and the external fluid is largely around the sides, but not always. Sometimes it actually wipes out part of the copper in the middle. Okay. I figured since one of the geophysicists is going to put up an equation, I thought I'd put up a chemical reaction just to confuse it. But chemical reactions are really important because as you dissolve one mineral, you liberate trace elements in that mineral, and that, depending upon the fluid chemistry, is going to get transported somewhere else. At the same time, as you precipitate a new mineral, you're going to actually add a series of different trace elements in that same spot. So you have the high temperature potassic or K-silicate alterations, largely driven by the magmatic fluid. You have the intermediate temperature, the hydrolytic to low temperature hydrolytic alterations, which are generated from the acid that's being formed, and you have the sort of neutral pH type reactions that are driven by the external groundwater fluid. So anyways, half of those are not balanced if you actually want to get down and figure it out, but I was being too lazy when I made the slide. Okay? And this just shows you that effect. In one rock sample from Red Chris, you got the high temperature K-silicate, so you'll have all the stuff that's happy at plus 500 degrees. You got the hydrolytic overprint, and so you're stripping out anything that sits in the mafic silicates. It's disappearing and going elsewhere, and then as the temperature decreases, you're stripping out even more. At the same time, you're adding a series of elements that are soluble at a higher temperature and ones that are at lower temperature. This is superposed on that, which is superposed on that. Okay? So, I seem to be missing a slide, but that's okay. Maybe it got out of order. It doesn't matter. And this is the distribution of elements that in rocks. This is rocks, not soils. This is rocks. So you have a series of magmatic fluids coming out. You're stripping a lot of elements out of the middle because they sit in the mafic silicates or in the feldspars, and they're being altered to a lower temperature mineral phase. So you're stripping things like zinc and lead and base metals, nickel, strontium, all that stuff that sits in feldspars and mafic silicates. They're being removed. And as that plume goes up, you're actually a whole series of Pathfinder elements that are somewhat distributed in a vertical sense. This largely, the distribution largely comes out of the Yerington district in Nevada, where you actually have 6 kilometers of the crust tilted on its side, and you can map that whole change in the field. Okay, the external fluid coming out here, in this case, if you have a source of chlorine, seawater, or evaporites, or anything like that in the sequence, it is a very toxic and nasty fluid, and it is stripping out a tremendous other sequence of elements because it's dissolving basically all these mafic silicates, and it's converting all the feldspars to albite, and it takes all these elements out, and it will leave behind additions of sodium, calcium, and of course lots of strontium. So depending upon whether you have a lot of chlorine in your fluid, you might get a whole overprint, as we will see a little later, of this alteration over this alteration. You get a whole mixed assemblage if you were just looking at it in a simple-minded way. Okay? So we know as you go up through the porphyry system, you can get different element associations at different levels in the porphyry. So from an exploration standpoint, understanding where you are within the hydrothermal alteration in geochemical space, you actually can get, use it to help you vector if you only have 3 outcrops or something like that. I won't go through it because it's in your slides, in your book, and you can read it better than I can describe it. Okay, well, this is a slide I thought I had. So really what we're coming down to is looking at the association of elements and hydrothermal alteration assemblages. So your copper comes out, you start to get moly when you get a halo of moly. When you're into the sericitic alteration, as you go up, you run through the whole 9 yards. And these are always the low temperature element association. So these are the elements I'm really talking about when I talk about Pathfinder elements that are not in the right place. Out where it's neutral pH, sort of rock buffered, you get the base metal zinc and manganese and silver and those things. So if you think about your normal porphyry zoning, you have your copper in the core, you have your peripheral lead, zinc, silver halos, and in the epithermal world, you have all those elements stacked up there. So that's in a system that is, in tech. Okay. So this is a diagram. I thought about this morning pulling this apart and rebuilding it, but I figured I'd probably run out of time to go through it. So I thought I would just leave what you have in the book. But basically, this is a base of till, top of bedrock, rock geochemistry using the 4-acid dissolution. Okay. So antimony, thallium, there's 2 thallium contours, arsenic, moly, zinc, copper. Okay, copper's here in the dash. Okay, antimony and thallium, remember they are the ones that have gone the farthest away. They're right over the top of it, as is molybdenum. So you got the whole suite of elements, which in some deposits is stretched out over 2 kilometers vertical depth. They're all sitting right at the same level right here. So if you had an acid, really acid-generated soil, you're not going to have any copper, you're not going to have any zinc, but you'll have all these other elements hanging around because they're stable in an acid soil. Okay? And the average person looking at that say, well, I'm in the epithermal world. And it's really not, because when because you have copper stick around, you're probably sitting above a porphyry copper system. I'll show you which it is in a minute. Okay? So let's go to a different one. Again, a little different suite, different scale. The last one was of a big district. This is of a deposit, or 3 deposits. So again, copper, and the copper level is much higher, 500 ppm. You're a lot closer. Zinc here, moly, strontium, and antimony. So if you remember back to the original diagram, the strontium is being stripped out of the level of the copper. It's gone because most of the strontium will sit in plagioclase. Plagioclase is altered to a K feldspar, and it disappears in most porphyries. But here we've got whacking rates amount of strontium, still stuck at the level of the copper. Okay. Likewise, you've got relatively elevated values of antimony in these bits here. That is also coming right through the middle of the copper zone. Okay, so it automatically tells you that there's something weird, something different has happened. It's not acting the way it's supposed to in the textbooks. Okay. All right, so the first example was red Chris. Okay. And we all know the success in drilling deep. This is quite a substantial ore body in the end. The east zone, the main zone, and the gully and far west zone here, quite a significant discovery, or at least success, in British Columbia. So let's look at the geology along one of these sections, and we'll come to grips with the elemental distribution. Okay, this is a work from a master's student, Jessica Norris, and there's a simple section in here, and there's a whole range of hydrothermal alteration assemblages. And on the side is the dominant iron-bearing phase. The color up here is largely kaolinite and illite. Okay, I'm telling you that's very, very low temperature alteration. In here is largely illite, down in here. And you got a bit of sericite or biotite and chlorite. And then down here, what's called magnetite, and that's your K-silicate alteration. Largely K-feldspar with a bit of biotite. But the copper goes all the way to the surface at 0.2, 0.3 right at the surface, or underneath the 6 meters of tip. Okay, so automatically you begin to see that there's a superposition of low temperature stuff over the high temperature stuff, and that's why you get low temperature elements over the top of the higher temperature elements. It's geology. Okay, I will give you a bunch of rock pictures just to show you. Here is the higher temperature alteration, lots of K-feldspar in the ground mass, hornblende going to secondary biotite. That's down, this bit's down in here, and that's a limit of almost pervasive stuff, but it actually continues virtually all the way to the surface, as well as in texture relic. You have the chlorite-sericite, aldehyde-type hornblends are going to chlorite, and then they go on to the white micas, and that's largely in this transition in these boxes here. That's the relic, and there's quite a lot of it up there. Then you get what we would typically call the philic or the sericitic alteration. There's just one little package of it exposed up there that hasn't been wiped out, where you see the pervasive pyrite with the white micas that are superposed over the secondary biotite. And then you got this late low temperature overprint, which actually you can find 1 kilometer deep in the deposit. It's everywhere. And it's what we call the intermediate geologic alteration, the alite kaolinite. Okay, so it is minus 260 degrees. So you look at them, and then you invert all the chemistry stuff and look at the assemblages versus their alteration package. Well, yeah, the copper's where it's supposed to, moly's where it's supposed to, zinc is where it's supposed to in terms of its alteration assemblage. And you go to the elements that are distributed about, and yeah, they sit with it where they're supposed to. You know, they're sitting out in this largely in the sericitic alteration, the arsenic, bismuth, antimony. Thallium and antimony and arsenic tend to go with the more lower temperatures, the alites and the sericite kaolinite. And it's just the whole thing. So everything, when you actually invert the chemistry and look at the rocks, along with the chemistry, elements are where they're supposed to be, but because of the superposition of the low temperature over the high temperature, you essentially got everything all in the same place. Okay? So that's the pattern. So it's a telescope system. A telescope system is a fancy term, the Dixilito coin, which really says that you got a low temperature hydrolytic alteration overprint on the higher temperature core of the system. So you end up with a different suite of elements than you would expect if it was in a normal vertical distribution. So let's go to the next one. The next one is from Bethlehem. And I know I neglected to thank the two companies that allowed us to do this work, Tech and I'll do Tech now because they're the most worrisome about that effort. And of course Imperial Metals at Red Chris. So there's the 3 porphyry pits. I've now got the geology underneath it, and the contours are still the same. The Eustis Jersey, East Jersey, and the Iona pits in here. And you can see that the antimony goes right across the Eustis pit. There's a bit here in the middle. There's out on the fringe, that's getting close to where it is. The zinc is where it's supposed to be, out on the margins. But it's these high strontium numbers and the elevated antimony, which are not where they're supposed to be because they should have been stripped out. Okay? So what really happened here is when you actually get down and look at the rocks, there is this sodic calcic alteration that's broadly mapped in here. A lot of this is waste dump, but it's broadly mapped in here with using the wonders of PowerPoint here to draw that. So it's not very accurately mapped, but nonetheless, it's here. And when you look at it in comparison to the geochemistry, you see that that's actually a very, very important overprint. And here are the rocks. Okay. Some of you can see a remnant of a little vein there. That's pyrite and chalcopyrite. This alteration is pretty toxic to sulfides. It will dissolve copper, it will dissolve pyrite, and it will make it disappear. So that rock has tremolite and probably a sodic oligoclase, and that's all that rock is. It started life as a granodiorite. So everything has been stripped out of that thing. And that sits right up there, and that's the zone of sodic calcic. So you can see all this white rock, was a little bit of pyrite left in there, so it's clearly weathering to goethite now, and you can broadly map the outlines of where the sodic calcic is streamed through the middle of the porphyry system. Okay? And you do the same thing. I won't belabor a lot of these probability plots, but here's copper. Copper sits in the strong sericite and the biotite K-spar. That's where it should. Zinc sits out with the sericite, out on the fringe. That's where it should. But if you look at the other elements that are not supposed to be there, Antimony sits in the sodic calcic. Of course, strontium sits in the sodic calcic. So the implications is the strontium, which is being stripped in these alteration assemblages, the K-silicate and the sericite, this is average rock, is being added back in a different phase. Okay, I can see I put Ken to sleep already. And so you've got elements that are being moved, and then similar elements are being replaced and put back into the system. So let me show you that this is not an unrealistic idea. This is stuff that we tried to get into the SEG newsletter a year ago, but it didn't fit according to time or thought about getting it in. So this is the Yarrington district. Okay, in here, it's a Jurassic complex. It's faulted along low-angle normal faults, and this piece used to sit on top of that and then rotated back to vertical. So it's quite a special geologic environment where you can actually get the whole 6 kilometers of outcrop in a porphyry copper deposit. There's no other place in the world that provides that opportunity. So what I showed you here is strontium. Okay? Strontium in rocks. Now, fresh rock should be taken with a grain of salt. It's fresh, like this. No rock in here is completely fresh, although sometimes you actually do see glassy plagioclase, which then you have a fair confidence that it's relatively fresh, but the hornblends in those rocks will be all chloride. So there's virtually every rock in here has seen a fluid at some point in time. So if you look at just the size of the dots, there are a lot of big dots down here. The little pale blue dots are ones that are really, really strong sodic calcic alteration. Likewise, and the porphyry system is here. You can see there's a lot of sodic calcic alteration deep. The other bit of Ann Mason system is here underneath this flat fault. And you can see there's a whole bunch of sodic calcic alteration up in there. So the fluid pathways are these dikes, and that's largely what we concentrated on when we did the sampling. Okay? So there's a lot of strontium moving around. The interesting thing here is when you actually go and look at arsenic. This is a very, very low arsenic system. You go up to the lithocaps that are still preserved, and there's virtually no arsenic. There's no gold either, but there's no arsenic. It's a very, very low arsenic system. But you can see the size of the dots is the relative concentration. That's not filtered at all. It's whatever came out of the assay sheets. Again, the Ann Mason system is here. Ann Mason system with other bits of here. And you can see, you know, there's largely not much. It's way below average crustal abundances down here. And you get right up into the sodic calcic alteration right at the edge. The 0.2 copper comes really close to those rocks, and you start to pick up in that alteration elevated concentrations of arsenic in sodic calcic alteration. So what is that? Well, we're not really sure, but we're strongly suspicious that what you're seeing is that interface, potentially the interface between the two systems. But if you're just looking at arsenic in your geochemical survey and not worrying about a lot of the other elements, you know, you're going to think one thing, and if you look at other elements, you might think something else. Okay. So I bring this back. I've made this blessedly short, I think, for the geophysicists in the audience. And the important point is the elemental distribution in porphyry systems. It's a function of rocks, the fluids, and the geology. Okay? They're built, it's a very, very predictable ore deposit model. Things belong in certain places, and elements belong in certain places. But they don't always all act the same way, and you can get different things, which I've tried to illustrate in this case. Okay? Again, it's a hammer and a hand lens, and you can do a lot of this in the field. And Pathfinder elements may turn out in your geochemical surveys in odd places that you don't expect them to be, but they can be explained as a function of the hydrothermal alteration assemblages and therefore the geologic history And it's really, is a plea as a geologist that you really need to pay attention to the rocks and the geology and all forms of technology, even if it's just the handlings and the hammer. So I'll end there now. I think I've got you on time and ahead of time. Question?
Time for some questions?
Yeah, but everybody, I had half the audience asleep, I could see that. It's right after lunch. That's why you put a rock talk right after lunch rather than a members talk? Yeah.
In your whole bunch of series of diagram, one element against what you call a normal score.
Yeah.
What's that?
Okay, those are probability plots that biogas puts out, and really that's you would below that most people would call that background.
Yeah, but what means normal score?
It's a normal score. It's a Peter. Do you remember what the formula is? Because I can never remember what the formula
It's
is.
looking at the average of the standard deviation and dividing the value, when you're subtracting the value from the average and then dividing by the standard deviation. So it's either going to be negative or positive.
Like Z-score.
It's like Z-score. Yeah.
Like
It's like
Z-score.
score against the actual value.
Is there a reason why you don't use percentiles or probability plot?
You can use percentiles, probably percentiles is that they fix them, whereas on this type of plot, this is doing the same probability plot. The slicing of intervals, the way you see breaks on intervals, do the same thing.
So you push the button and I can. I'm just kidding. Yeah, Peter, Alan.
Yeah. I've got a question, and I've been wondering about this for a while. Like, we always see these pictures of very large volumes of fluids moving through solid rock. And I'm just wondering how that happens. It must be entirely along fractures.
Absolutely.
High permeability.
Absolutely.
And then if it is, how do you reconcile that with your sampling of the rocks? Because it would vary tremendously whether your sample had a little bit of permeability or if you're in the massive rock in between.
Okay, so I mean, that's a really good point, and it's a point that I did forget to mention. So thanks, Alan. You're right. I mean, fluid flow is concentrated in the permeability fabric. It's going to be fractured dominantly, but there is some intergranular, but that's way slower, much slower than anything along a permeability. So in any sort of hydrothermal system, okay, where you get pervasive alteration, all that really tells you is you've got a lot of little cracks. Fluid can go through because the diffusion normal to the flow path is a lot slower. So if you got a huge zone of pervasive alteration, you actually probably have a lot of little cracks that they're completely healed now. Okay, so the sampling protocol here is we always went in, because we were doing rocks that were at the surface, and these are not deeply weathered because you can in places still find fresh pyrite, sulfide at the surface. So we actually because what we wanted to do was what's the distribution. So, and because we know what the hydrothermal alteration, we specifically at each point went after the most altered rock. Now, if you look at it and think about it in a soil survey, then you're going to have a hydromorphic dispersion halo around that, and their values won't be the same, of course, but in a normal system, they will be somewhat distributed in a similar manner.
You don't need a bulk sample.
Pardon me?
You don't need a bulk sample.
This size is all we took. Yeah, I mean, you had to carry the damn thing. You know, there's no roads everywhere, so we had to limit what we could carry. Tom?
Yeah, a lot of all these trace elements you see, I guess they're a result of being able to do ICP, MS,
Yeah.
geochemistry.
Yeah.
And a lot of the big discoveries were made, let's say, for example, Escondida, probably before that was available.
Mm-hmm.
What kind of methods were they using to find, you said rock chips and that sort of the soils?
Yeah, they were, I mean, well, at Escondida, for example, they did have hills sticking out.
Mm-hmm.
And they did have they did rock sample there, but they were using the values at the time,
Right.
and I mean an analytical package at the time, and the detection levels were high.
Yeah.
Okay, with the advantage of the modern analytical packages, and we went for the lowest detection level, because what we wanted to do was get the biggest halo that we could actually map. And the advantage of those, if you go to the proper analytical package, you can get things below average crustal abundance. And if you don't worry about background in the initial stage, you know, if you go 10 times average crustal abundance, that's usually pretty anomalous. And for some of these elements here, average crustal abundance is virtually nothing. And so when you start seeing them, and then when you see them and whether they move in a soil profile, and depending on the composition of the soil, you'll get different results. And some will be bumped up. Some guy showed me one where you had this, you know, hundreds of ppm of thallium in a rock, not a rock, but a really weathered zone. And it's because everything else was stripped out, and that was one that stuck around. I mean, I don't know, that's toxic, 170 ppm of thallium.
Dick, I was wondering, the system now is on its side.
Yeah.
How long, or was it long enough when it was vertical, I assume it was,
Yeah.
that you can tell the difference between the weathering that was in the column was vertical versus when it tipped over? You would not be able to?
No, you can't. There is no, you can in one place. The Yarrington mine itself, actually, in the tertiary, at I don't know, 27, 28 million, it was in the bottom of the big Paleo Valley, and it had a very, very small supergene enrichment zone on it, and with a bit of a leach cap over the top. And in places you can see it's a variable thickness. So in the system, it actually was tilted a bit, and even in the Jurassic, and then it was tilted a bit more, and then it was really tilted, you know, gangbusters after the volcanics came in. So the volcanics actually sealed the system, and the weathering has been going on for the last, 14 million years. And it's taken all the upper plate tertiary volcanics off. And so I would expect that it's actually been exposed to the surface, since the glaciers. Because there's a lot of exotic copper that you see down the hydraulic gradient, and that exotic copper has, it's got a date from the pluvial times. There are no glaciers in this part of the world, so we're much better off down there than up here in Canada. We don't have to tell.
And the final rotation, was it the basically
Yeah. So Charles, I invite you to come to the Yarrington mapping course. We got at least one person that's done it. We do it every year. We've had a couple of them. 420, 450 industry geos that have come through it. And we walk through the entire geology, the entire alteration assembly, from bottom to top, and make you make a map. Well, heaven forbid.
And I'm not reminding you, Dick, you probably remember, but when the last time that it was you and Haley and there was one, what's his
John
name?
Dillis.
John Dillis. I was, recruiting papers. I had been doing some background work for another project through Camaro on compiling aeromag signatures over porphyries. And I just mentioned to Dick, I said, well, he, obviously very knowledgeable of Yarrington. I said, of course you've seen the aeromag image. And he says, what? And this is the story. This was done in 1975 by
Actually,
Anaconda. But it's not part of the mapping course, but it should be.
I had seen U.S. deals, but I hadn't seen your version of it.
So hopefully, if he does it again and if he's enticed, he might have a look at the aeromag image to go with it as well. So, anybody else? I think it's good.
Tom?
Oh.
In the example, with lithocaps, how are they detecting the signals of good systems below?
Well, in the lithocap, I mean, there are people. There's the whole program that's going on in Australia about claiming that they can, that's the claim. I haven't looked at the data, or do I have an opinion? Claim that they can map out where you should drill to get the hotspot. And it works the same way, in a very similar way. There are elements, it's all based upon the solubility in fluids, which is a large temperature function, and looking at the minerals that hold those elements, And they've got a paper on Lepanto, and it's all based upon the lead and strontium in alunites, for example. And then also the shortwave infrared, the spectral changes that go with with those substitutions. And what I didn't show in here is all that bit, which is the spectral shifts that you see. I didn't want to confuse Kim.
So, one beer at lunch, man. That's all. All right, thanks, Dave.
Thanks a lot. Great.